Hello and welcome to Relatable Code. In this video, we're going to talk about coroutine contexts and dispatchers in Kotlin. So let's get started. As you already know, coroutines in Kotlin are a powerful feature designed to simplify asynchronous programming by making asynchronous code sequential and more readable as well. They enable developers to write clean and concise code for complex asynchronous tasks such as network requests, database operations, and long-running computations without blocking the main thread. Okay, and this results in applications that are more responsive and efficient as well. Coroutine contexts and dispatchers are fundamental concepts within Kotlin's coroutines. A coroutine context includes various elements, but a dispatcher is one of the most important because it defines the thread or set of threads on which the coroutine should run. Okay, and dispatchers manage how and where the coroutine's code executes, whether on a single thread or a pool of threads, or even on the main application thread, thereby significantly influencing the performance and the behavior of the application. We have already seen the Dispatchers.io in action, and we use it like this. We wrote coroutine scope, which is one way of launching coroutines. We will explore other ways in future videos. And we use dispatchers.io.launch. And inside this launch block, we used suspend functions, like, for example, get user data, which can delay for 1 second, for example, before printing out a message like retrieved user data. Okay, and we used that suspend function in the context of this dispatchers.io. Okay, but I haven't told you about dispatchers.io yet, and that was the only dispatcher that we covered in the previous videos. Okay, so in this video, we're going to see the difference between Dispatchers.Main, Dispatchers.io, and Dispatchers.Default, in addition to Dispatchers.Unconfined. Okay, and we're going to start with Dispatchers.io. The I/O dispatcher in coroutines is one of the most used dispatchers, and it's used to dealing with I/O tasks, which means input-output tasks. Okay, and by that we mean tasks like network requests, database operations, or maybe even disk reads and writes, or file manipulation, for example, reading and writing into files. Those are called I/O operations, and they are the kind of operations that will block the thread until they are completed. Okay, and that's because these operations will take some time to execute. When you want to execute a network request, you have to wait for a response to be returned from the network server. Okay, same thing goes for the database operation, where you're trying to, for example, retrieve some data from a database, and the same goes for the other operations as well. Okay, those are I/O operations, and we deal with them in coroutines by dispatching them to the I/O dispatcher. Okay, that's why that dispatcher was made, and it's very essential. Okay, you need to know how to use that to ensure that these requests or tasks don't interfere with your app's UI. Okay, so that you can maintain a smooth application experience for your users. This I/O dispatcher is used to offload those blocking I/O tasks to a shared pool of threads. Okay, so it doesn't deal with a single thread, it deals with a shared pool of threads, which allows for efficient I/O operations that don't block the main thread. Okay, under the hood, this thread pool dynamically adjusts to this workload. It starts with a core number of threads and can expand up to a maximum limit, where more tasks are submitted and existing threads are busy, if that happens for any case. Okay, and this expansion allows for handling a large number of concurrent I/O operations. However, to prevent excessive resource consumption, it scales back when the threads are idle. Okay, so when you offload some tasks to this pool of threads, when any one of those threads finishes executing the task or is suspended for any reason, it will be considered an idle thread and can receive a new task. Okay, it's very efficient in that way, and it really enables you to deal with a lot of these I/O operations, which you will have to do a lot in Android development. And next, we have Dispatchers.Main. The main dispatcher is specific to applications with a user interface like Android applications. It's confined to the main thread of the application, and it allows for direct interaction with the UI. Okay, so unlike the I/O dispatcher, it only deals with that one thread, which is the main thread, and it's used to handle those UI updates. Okay, you can utilize this dispatcher for any operations that need to update the UI or interact with UI components, which ensures that these actions are performed safely on the main thread. The mechanism of Dispatchers.Main is straightforward. It schedules tasks to run on the application's main thread, which in Android is the UI thread, and it ensures that all coroutines which are launched in this context execute their code on this single thread, which makes it safe for UI operations. Okay, because you can't actually modify any UI components in a background thread, you have to do it on the application's main thread. Okay. When using coroutines, you can start a block of code in the I/O dispatcher, and you can then continue it inside the main dispatcher. Okay, and I'm going to show you how. For example, in our case, we can start this suspend function in our I/O dispatcher. We can have it return a string, for example, which can be this retrieved user data string. And we can do it like this. Okay, so currently, this function is executed in the I/O dispatcher, and it retrieves a string. Okay, so you can assign this string to a value for user data. And I'm going to show you how we can update the UI after retrieving that user data. Okay, so inside our activity_main XML file, we can drag and drop a text view right there. We can name it something like TV user data. And we can initially remove the text of that text view. Okay. And here inside our main activity Kotlin class, we're going to use this user data to place it inside our text view. Okay, and we can do that by switching from the I/O dispatcher to the main dispatcher, which we can do like this. You can use a function called withContext, and in withContext, you can specify Dispatchers.Main. Okay, inside this dispatcher, you can now reference your text view, and you can assign not the text view itself, just the text of that text view. Okay, you can assign user data to the text of that text view. And that's about it. You can run your application and check it out. So start your emulator. And there you have this retrieved user data, which gets simulated after a second. That was pretty short. Let's increase it to 2 seconds so that you can see the delay which happens. So that's our application, and that's our retrieved user data. Okay, that's how you can launch a coroutine in one dispatcher, and you can then continue it inside another dispatcher. And that's the main reason why you will use the main dispatcher. Okay, you will execute those long-running operations in the I/O dispatcher, whether it is a network call or a database operation or any other I/O task. And after that, you're going to want to update your UI components, which you have to do inside the main dispatcher. Okay. And next we have our Dispatchers.Default. The default dispatcher is optimized for CPU-intensive operations. It also uses a shared pool of threads like the I/O dispatcher, but it is specifically intended for computational work that can be run in a parallel manner. Okay, so we're talking about tasks which require substantial computational resources, like processing large data sets, performing complex algorithms, or any work that's CPU bound. Okay, this can also be something like processing a large image, maybe sorting a large list of data. Tasks like that should be done using the Dispatchers.Default to avoid blocking the main thread and to utilize the CPU resources effectively. Under the hood, this Dispatchers.Default dynamically manages a pool of threads, but it's based on the number of available CPU cores. Okay, by default, the number of threads which is used is limited to the number of CPU cores with a minimum of 2 threads to ensure that we can execute our task in a parallel manner, even on single core devices. Okay, and finally, we have the unconfined dispatcher, and it's a special dispatcher that's not confined to any thread. Okay, it starts the coroutine in the caller's thread, but after suspension, it resumes the coroutine in whichever thread the suspending function is executed on. This type of dispatcher is not used very often because it's unpredictable. It's used either for top-level coroutines that don't interact directly with the UI or perform any blocking operations. It's most often used in testing environments from my experience. Okay. If you like my type of content and you find it to be relatable, please don't forget to leave a like and subscribe for future content, and I'll see you in the next video.